Building, transporting, and installing giant wind turbines combines engineering, teamwork, and precision, turning massive steel and blades into clean energy towers, shaping a sustainable future. In 2018, the Steam Turbine Design Office in Elblag celebrated its 70th anniversary, marking decades of innovation since 1948. Now part of GE, it continues creating advanced turbine solutions, combining cutting-edge engineering, digital technologies, and global expertise to deliver efficient industrial performance worldwide. The construction of foundations for onshore wind turbines is a critical stage in ensuring the stability, safety, and long-term performance of the installation. At Glenaffe Wind Farm in County Tipperary, Ireland, this process involves creating massive reinforced concrete structures capable of anchoring turbines and effectively transferring loads to the ground. Typically, these foundations take the form of either large gravity slabs or piled systems, with the choice depending on turbine size and local soil conditions. The construction process begins with site preparation and design, during which engineers analyze the geotechnical conditions and determine the required type and depth of the foundation. A reinforced gravity base is often preferred when soil conditions allow, while piled foundations are adopted for weaker subsoils. Once the design is finalized, the site is cleared, leveled, and marked for excavation. Next comes excavation, where earth is removed to the required depth and width, creating the cavity for the foundation. This step is carefully monitored to ensure proper alignment and stability. Following excavation, the reinforcement phase is undertaken. A dense network of reinforcement bars is placed, along with a steel anchor bolt cage that will later serve as the critical connection point between the foundation and the turbine tower. This cage is positioned with precision to maintain alignment for tower installation. The most crucial step is concrete pouring, where high-strength concrete is delivered and poured into the foundation cavity. For large foundations, continuous pouring is often performed to avoid cold joints and ensure uniformity. Once poured, the concrete is compacted and leveled to form a solid mass around the reinforcement and bolt cage. Afterward, the curing process allows the concrete to gradually gain strength and durability. Proper curing ensures the structure can withstand the immense static and dynamic forces generated by turbine operation. Finally, once curing is complete, tower installation begins. The turbine tower base is securely bolted to the embedded anchor cage, ensuring a firm and lasting connection. Through these stages, the foundation provides the stability required to support wind turbines, enabling the reliable production of renewable energy at Glenaffe Wind Farm. The construction of wind turbines at Phong Dien 1 Binh Thuan Wind Farm during Phase 2 involved a crucial stage dedicated to the pouring of reinforced concrete for the turbine foundations. This stage was one of the most significant in the project, as the entire stability of each wind turbine depends on the strength, quality, and durability of its foundation. The process began with the placement of large quantities of ready mixed concrete, delivered to the site using concrete mixer trucks. The trucks discharged the mixture into designated areas within the formwork, ensuring that the foundation cavity was gradually filled from bottom to top. Since the foundation was designed to support the massive weight and dynamic loads of the turbine tower and rotor blades, the pouring operation required both precision and consistency. A network of pumps and flexible hoses was used to guide the concrete into place. Workers carefully controlled the flow to prevent segregation of the mixture and to ensure full coverage around the embedded reinforcement steel. At the same time, vibrators were employed to eliminate air pockets and achieve maximum compaction, thereby increasing the density and long-term strength of the concrete mass. This stage was not only a test of engineering, but also of coordination. Continuous pouring was necessary to avoid the formation of cold joints, which could weaken the structural performance. Therefore, the operation was carried out in a planned sequence, with teams working simultaneously to maintain a uniform pace. The weather in Binh Thuan, often sunny and windy, was also monitored closely, as temperature and humidity could affect the curing of the material. After the foundation cavity was completely filled, the surface was leveled and smoothed to prepare for subsequent steps. However, the most important requirement at this point was patience. The freshly poured concrete had to be left undisturbed for an extended curing period, allowing it to gain sufficient strength before supporting any further construction. During this waiting phase, the foundation was regularly watered and protected against environmental influences to prevent cracking or shrinkage. This stage of pouring and curing concrete was the backbone of the entire wind turbine installation. The impressive operation of loading a huge wind tower section onto the SS Badger on September 25, 2012. This task highlights the scale and complexity of transporting components for modern wind energy projects. The massive cylindrical section of the tower, designed to support a wind turbine, is carefully positioned on a large trailer pulled by a powerful semi-truck. Due to its size and weight, the process requires precision, coordination, and specialized equipment to ensure both safety and efficiency. A transport crew guides the truck as it slowly maneuvers toward the ship's barge ramp. Every movement is closely monitored, as the limited space demands accuracy and controlled speed. The wind tower section lies horizontally on the trailer, secured to prevent shifting during the loading process. Once aligned, the vehicle gradually enters the SS Badger's barge, marking the start of its voyage. This operation demonstrates not only the engineering challenges of handling oversized cargo, but also the essential role of maritime transport in delivering renewable energy infrastructure across regions. The transport of the final wind turbine tower segment, carried out by Turlinden Transport, took place on the nights of February 12 and 13, 2013. This operation represented the last stage in the delivery of the massive tower sections required for a wind power installation. Because of their exceptional length, width, and weight, the tower segments demanded a carefully organized logistics effort that relied on nighttime movement to minimize disruption to daily traffic and ensure safety along the transport route. A specialized heavy-haul convoy was deployed for this purpose. The convoy included a powerful tractor unit pulling an extended multi-axle trailer, specifically engineered to handle the extreme loads of the tower segment. The nighttime schedule allowed the vehicles to travel through towns and along regional roads with reduced traffic density. To secure smooth passage, escort vehicles accompanied the transport, guiding the driver and providing real-time coordination with authorities and road staff. One of the most remarkable challenges of the operation was the need to temporarily remove road signs and other obstacles along the route. These structures often restricted the available clearance and would have obstructed the oversized cargo. Escort teams worked systematically through the night, dismantling and later reinstating signs to allow the convoy to advance without incident. This precise coordination ensured that infrastructure was protected while still enabling the successful delivery of the component. By the end of the journey, the last tower segment had reached its destination, marking the conclusion of a complex and demanding transport sequence that highlighted Turbine Transport's expertise in handling extraordinary logistics challenges. The construction of a wind turbine foundation is a demanding process that requires precision, heavy equipment, and careful planning. At the project site, approximately 500 cubic meters of soil are excavated to create the massive pit needed for the base. Once the excavation is complete, a 15-ton anchor cage is delivered and carefully positioned in the center. This steel cage serves as the core structural element, anchoring the turbine tower and ensuring stability against high winds. To further strengthen the foundation, workers install 66 tons of reinforcing steel within the excavation. These reinforcements are arranged in a detailed grid, designed to distribute loads evenly and prevent cracking. After reinforcement, the pit is filled with 523 cubic meters of high-quality concrete, which is poured and compacted to eliminate voids. The result is a solid, durable foundation capable of safely supporting the wind turbine throughout its operational lifetime. On Monday, the 11th of February 2013, the individual components of the massive crane arrived in Oldus, marking the beginning of an impressive assembly process. The following day, Tuesday the 12th of February 2013, work continued as the Liebherr LG 1750 crane was systematically put together on site. Each section was carefully aligned and connected, ensuring precision and stability for the structure. By Monday the 12th of February 2013, the crane was fully erected, reaching an impressive height of 139 meters. The LG 1750, a powerful lattice boom crane, was prepared for heavy lifting operations with its trackless configuration. The assembly showcased the coordination, expertise, and technical skills required to build one of the most advanced cranes in the world, ready to take on demanding construction challenges. The installation of the Senvion 3.0M 122 wind turbines at Lussac-les-Églises in France marked an important achievement in renewable energy development. The project consisted of 6 turbines, each with a rotor diameter of 122 meters, specially designed for sites with low wind conditions. Together, these turbines provide a total capacity of 18 megawatts, generating enough electricity to power approximately 6,000 households each year. One of the major challenges of the project was transporting the exceptionally long 60-meter blades through narrow village roads and wooded areas. To overcome this, the Senvion France team employed an innovative transport system known as the blade lifter. This equipment allowed precise maneuvering of the blades by adjusting their tilt and orientation, ensuring safe delivery to the construction site without damaging infrastructure or the environment. Once delivered, the components were assembled using large cranes to erect the tower sections, nacelles, and rotors. The successful installation at Lussac-les-Églises not only highlights engineering expertise, but also demonstrates how innovation in logistics can make wind power projects feasible even in challenging locations. Ultimately, the wind farm represents a sustainable energy solution that benefits both the local community and the environment. The installation of a giant GE wind turbine in Vang at the wind test site field in the Netherlands marks an important step in the country's renewable energy development. The project involves assembling a tubular steel tower with an impressive hub height of 131 meters. This towering structure serves as the foundation for the massive rotor system, designed to harness wind power with maximum efficiency. Beside the tower, the turbine's blades stand out as another remarkable feature. Each blade measures 67.2 meters in length, giving the turbine an overall rotor diameter of 137 meters. Such a span allows the machine to capture greater amounts of wind energy, even at lower wind speeds, which directly translates into higher productivity. The scale of these blades highlights the continuous advancements in engineering, as longer blades are essential for increasing energy output. Once the blades are carefully hoisted and attached to the hub, the system is combined with GE's upgraded generator, which has been increased to 3.6 megawatts. This enhancement enables the turbine to deliver significantly higher annual energy production compared with older models. As a result, customers benefit from improved performance, better cost efficiency, and a stronger contribution to sustainable power generation. The installation process itself is a complex operation, requiring precision lifting, secure bolting, and rigorous testing. Specialized cranes and expert teams work together to ensure every component is safely mounted and aligned. In the end, the completed turbine not only stands as a symbol of advanced technology, but also represents a major investment in clean energy for the future of the Netherlands. At Chaudière Falls, the powerhouse is designed to harness the river's energy through 4 hydroelectric turbines. The installation of one of these advanced 8-megawatt units, known as eco-bulbs, demonstrates both precision and scale. First, the massive turbine components are delivered and carefully lifted into position by cranes. Due to their weight and size, every movement must be planned with accuracy to ensure safety and alignment. Workers then secure the turbine into its concrete housing, where it will interact with the flow of water to generate electricity. Once connected, the unit is integrated with the powerhouse's systems, linking mechanical energy to electrical output. These EcoBulb turbines are specially engineered for high efficiency and sustainability, providing renewable power while minimizing environmental impact. The process highlights the complexity of modern hydroelectric technology and its role in clean energy production. The robotic wind turbine inspection process begins by placing an autonomous robot on the surface of a multi-million-euro turbine blade. Designed with lightweight materials and an anti-slip structure, the robot can operate reliably despite strong side gusts or vibrations from the wind turbine blade. It uses industrial-grade vacuum cups for secure adhesion and high-power density DC motors, combined with high-performance pneumatics, to ensure stable and precise movement along the blade surface. The control system is engineered to handle worst-case failure scenarios safely. With simultaneous inspection capabilities on both sides of the blade spar, the robot performs comprehensive evaluations without repositioning. Its navigation system allows consistent movement and accurate data collection even on curved surfaces. This advanced robotic system enables fatigue life assessment of wind turbine blades in less than 4 hours, offering a fast, reliable, and automated solution to structural health monitoring in harsh and dynamic environments. The Kansas Wind Turbine Project highlights the expertise of Northwest Crane Service and the advanced capabilities of the Liebherr LTM 1750-9.1. For decades, the company has specialized in moving large structures, combining teamwork with state-of-the-art technology. The arrival of the LTM 1750 completed their fleet, offering significant advantages thanks to its high lifting capacity, rapid setup, and mobility compared to crawler cranes. At the wind farm, every turbine plays a crucial role in supplying electricity to surrounding towns. When a turbine goes offline, production stops, so speed and efficiency are essential. The crew carefully positions the crane within tight site access, assembles it, and rigs it up in just a day, a process that older machines would take much longer. Using advanced electronics and Bluetooth-controlled outriggers, the crane ensures precise, smooth, and safe lifting operations. Safety is a top priority, with strict tie-off systems and streamlined assembly steps reducing risks for riggers. The project not only demonstrates the crane's environmental advantages requiring less fuel and fewer truckloads, but also the strength of the Northwest team. Family-oriented values, professionalism, and high standards define their work ethic, ensuring turbines are restored quickly. Together, skilled people and cutting-edge equipment make each lift efficient, safe, and reliable. On Saturday, February 16, 2013, the assembly of the hub and rotor blades for a wind turbine took place. This stage of installation is one of the most critical, as it involves connecting the massive blades to the hub that transfers wind energy into rotational power. First, the hub was carefully lifted by a heavy-duty crane and positioned in front of the nacelle. Technicians ensured precise alignment and secured it firmly. Next, each rotor blade measuring several dozen meters in length, was individually hoisted and attached to the hub. This process required slow, steady movements as the blades had to be maneuvered into place with millimeter accuracy despite their weight and size. Once all three blades were connected, the complete rotor assembly was prepared for lifting. Finally, the rotor was raised and mounted onto the hub, completing a major milestone in the wind turbine's construction. The alignment of the low-pressure steam turbine inner casing is a crucial step in thermal power plant maintenance. First, the casing is carefully lowered into position using lifting equipment. Precision instruments such as dial gauges and laser alignment tools are applied to measure and adjust its placement. Technicians ensure concentricity and correct clearances with the rotor to avoid mechanical stress. Once the casing is aligned, it is securely fastened and rechecked for accuracy. Proper alignment guarantees turbine efficiency, smooth operation, and extended service life. The construction of the first utility-scale wind farm in the United States marked a major milestone in renewable energy. At first glance, each turbine appears identical, with its own road, foundation, and tower, yet the process is far from simple. Behind every unit lies extensive planning, manufacturing, and teamwork. In this facility, hubs and machine heads, the essential engines of wind generators, are produced, supporting both clean energy and job creation. The project stimulates local economies, providing opportunities for small businesses that might not otherwise survive. It also generates thousands of construction and manufacturing jobs nationwide, not just operational roles. Building a wind farm means working together, overcoming weather challenges, and constantly finding solutions. Beyond clean power, it delivers pride, stability, and a vision for the future. Ultimately, these wind farms embody the American spirit of innovation, community, and sustainability. Saucercid is a major port operator, offering specialized services across 3 terminals: the dry bulk terminal, the steel products terminal, and the breakbulk and heavy lifts terminal. The company is capable of handling all types of breakbulk cargo, including oversized and heavy units. It operates the largest ro-ro ramp in France, designed to accommodate parcels weighing more than 800 tons. Examples include tanks of 566 tons and 26 meters in length, as well as 40-ton units measuring 15 meters. Operations include unloading from FOT to the quay using shore cranes and loading onto vessels with ship cranes. The handling operation for the ITER project involved lifting a component weighing more than 500 tons. Using a powerful port crane, the massive load was carefully hoisted from a barge. Precision and safety were essential throughout the process to ensure flawless execution. Once lifted, the component was gently lowered onto a self-propelled modular transporter, which enabled its secure movement on land, marking a crucial step in supporting the ITER project's ambitious energy goals. Port of Blyth is one of the UK's leading offshore energy support bases, trusted by the world's top offshore companies. The port offers 15 kilometers of high-quality berths across 4 ISPS-compliant terminals, accommodating vessels up to 35,000 DWT at berths with 9.5 meters draft. It provides advanced heavy lift mobilization and demobilization, full project support, and licensed decommissioning facilities. With 35 hectares of quayside development opportunities adjacent to deep water, the port continues to grow. As a trust port, all profits are reinvested into expanding facilities, including its unique quayside wind turbine training center,